Um, Chapter 6 is going to be on the topic of thermochemistry. Uh-oh. You want to take the exam in person?
It's my math test.
Oh, you already took it online?
Yeah,
Oh, okay.
because I knew I was gonna be late because I
Yeah.
had math class and she took longer. So I'm
Okay.
gonna take it yesterday, if that's okay.
No, that works out perfect because I'm just now starting the lecture on chapter 6. And there's, yeah, one of each. Okay, thermochemistry. Like hope I've often said is you can learn a lot from tearing a word apart. We know what chemistry is. Thermo refers to heat. And it's actually uh, it can be more involved than that. There's a branch of chemistry called thermodynamics that really gets into this side of the chemistry equation in much, much more detail. In fact, it brings in a lot of physics too. We're not going to go that deep. This is kind of an introduction to thermodynamics, and gives you more of a practical approach of how to deal with heat that's generated in in a reaction or absorbed in a reaction. All right, so we'll start with the basics. All right, anybody remember definition of energy from grade school? Or is it just me? Capacity to do work or to produce heat. That's what energy is. The rest of the universe, if it's not energy, is matter. And this is one of the cornerstones of our investigation of thermochemistry is the law of conservation of energy. Energy cannot be created or destroyed, right? The energy, this is the assumption. The energy that the universe started with is the same amount of energy the universe has now. The only thing that's happened is we've converted from different forms. It's just undergone different forms. And this is part of thermodynamics, so what you're not going to get too deep into is the usefulness of energy. Right? There's energy that's very useful, and if you extract some work from it, then it becomes less useful and less useful. But still, that energy is converted from one form into another. And then, of course, I hesitate to mention this, but Einstein proved that energy and matter are interconvertible. E equals mc squared. Yeah. Um, we're not going to go there. This is actually the first law of thermodynamics. So this is the only one we're going to deal with. There are actually there are 4 other laws. There's a second and a third, and then they figured there was one that was preceded the first one, so they made it the 0th law. But we're focusing on the first law. The total energy of the content of the universe is constant. And the way we express that mathematically is to say delta E of the universe. Okay. Any change in the universe energy is equal to 0. In other words, before and after are the same values. All right. There are very, very, very rare chemical or physical processes. And we include physical processes there because we have to, that do not involve a transfer of energy. It's very rare to find them. Nearly all chemical or physical processes that we know of involve a transfer of energy from one place to another or from one form to another. Okay. One way of organizing what we know about energy is to divide it into two types. We have potential energy. And this is under the general heading of energy. Potential energy and kinetic energy. Kinetic energy should be easy to understand. If it's moving, it has kinetic energy. Right? All you need to do is show that something is moving relative to something else, and it has this energy that we can define by this equation. Right? If it has a velocity of any kind and it has a mass, then it will have kinetic energy. Potential energy, on the other hand, can be defined in several different ways. Positional, based on its position, and I need to tell you what we mean by that. Based on its position where? In a gravitational field, right? Like on the surface of the earth, or elevated to 1,000 feet, or just to get on top of the building. If you, in order to move from this position to a higher level in this gravitational field takes energy. I mean, I have to climb stairs, a ladder probably, to get on the roof. And I've added potential energy to myself based upon my position. Now, since the first law is still operative and all energy just changes places, I can get all that energy back, right? I can do it slowly or I can do it quickly. Right? If I do it quickly, I just jump off the roof and hit the ground. And when I hit the ground, I get that energy back. Now I have kinetic energy. You know, I'll be gathering speed as I drop, but then all that kinetic energy is converted back into heat, potential energy, when I hit the ground, if I survive. Okay. We can also define potential energy based upon composition. And this is where chemistry fits in. Energy can be stored in chemical bonds. My favorite example is nitroglycerin. Right? When you take the glycerol molecule and you attach nitrates to those three positions on that glycerol, you do so by putting a lot of strain on those bonds. And there's a lot of energy stored in those bonds. That's why you just have to look at nitro. If it's pure liquid nitroglycerin, just look at it cross-eyed and it'll blow. It's very unstable. But there's a lot of energy stored in those bonds. So that's chemical energy stored in bonds. We can also store energy electrostatically. If we have a positive or a negative charge, if we have, say, two positive charges close to one another, they're going to repel. If we hold them there, then we've stored energy. If we bring them together, you can feel the push as they get closer and closer and closer. The closer you get them, the more energy it takes to put them together. And then if you want that energy back, just let them go and they go. Okay, that could happen with two negatives also. Or if we had a positive and a negative, then they want to attract. So to get them further apart, we just have to pull like that and store energy in their electrostatic attraction. And then if we want to get that energy back, just turn them loose and they go right together. Do the same thing with magnets. Right? We can have magnetic, similar to electrostatics, two north poles, right? They'll repel unless you push them together. Or have you ever played around with these rare earth magnets that come out of hard drives? Or you can buy them now. I've got some on my refrigerator. They got little knobs on them. They're easier to handle. But once you get them close to something that's ferromagnetic, it'll go And if you get your finger in between two of those magnets, you get a hell of a pinch. They're attracting each other, and we hold them apart. That stores energy. So there's magnetic storage, elastic energy, right? I don't know about girls, but as little boys, we used to make these, take a stick and carve it a certain way, and then we strap a clothespin on one side. My brother put his on one side. I put mine top, right, and left. And then you carve a notch in the end, and then you get a rubber band and you hook it in that notch and bring it back to your trigger, right? So he only had one shot. He had to reload. I had 3 shots, so I always won. That's storage of elastic energy when you pull that rubber band tight. There's thermal energy, right? We mentioned that one earlier. If something is really, really, really hot and you can make steam from it, then you can run it through either a piston engine of some kind, like on the old locomotives, or you can run it through a steam turbine and run a generator and extract energy from it. And it'll be, when it goes in really hot and under high pressure, it'll come out low pressure and cooler. We've extracted some of that energy out of it, but it has potential energy based upon its heat content. And then last but not least is nuclear. There's a lot of energy stored in the nucleus of atoms. Some of them are more accessible than others, like uranium-235, a very unstable nucleus. It will split into 2 smaller pieces, and when it does, it converts some of its mass into energy. And that's where that nuclear energy comes from. Or if we bring 2 protons together, right, and make helium, let's see, that would be, it works better if we have 2 of these. Yeah, 2 of these, like that. Then it makes 4. This is 1, this is 2. The helium that is produced from this reaction, when you bring these 2 nuclei together, the helium weighs less than these 2 together. And that difference in mass is converted into energy. That's where the sun makes our energy. It uses helium. And it's more complicated than that, but you get the idea. Those are all potential forms of energy. All right, let's focus on kinetic energy now. Kinetic energy is, like I said before, due to the motion of any mass. And actually, there's some crossover here, because you can include thermal energy in kinetic simply because of molecular vibrations. They may not be moving far in either direction, but they are moving, so they do have energy. And that energy we recognize as heat. Now, of course, once you get the material, if it goes from a solid to a liquid to gas, once you get it to a gas, then those individual molecules, they're moving lickety-split their own directions till they hit each other. Right? So then you do have translational motion in gases. That's definite. Okay, and there's your equation. You can calculate the kinetic energy of anything if you know its velocity and you know its mass at any one instant. Now, when we transfer kinetic energy, and now we're going to sort of blend these together. what we see in this example is that that ball A is being held in position. We don't know how, but it's being held there. And then B is sitting down below. Now, if A transfers its energy to B, then A should end up at the bottom. And where should B end up? On that top level, right? That's equal height, right? If it's a perfect transfer of energy from one. So A's potential energy becomes kinetic right before it hits B. It stops, transfers its kinetic energy to B, and B then takes its kinetic energy and makes it into potential energy of position, right? That's the ideal situation. Here's what really happens. B doesn't get all of it, right? Some of it is lost to mostly heat, right? This molecular vibration. Some of that energy heats up B and A both, and it loses some of the energy, so it can only go up to the first level. Okay. Let's see. All right, we need to clarify something that I think I put this slide in there because I don't think your book clarifies it enough or makes it obvious. The difference between temperature and heat. They're related, right? And we use temperature differences to calculate heat content, right? But they are different measured values. Temperature is an intensive property. And what we mean by that, intensive. That just means if you measure the temperature of an object or a mass of something, it's uniform. It has a uniform temperature. Measure it here, same temperature as here as here. If you have this much of it and it's at that temperature, or you can have this much at that temperature. It doesn't matter how much you have. The temperature is independent of the amount. Okay. Heat, on the other hand, is extensive property. It does matter how much you have. If you have this iron ball like that at a given temperature, let's just say 50 degrees Celsius, and you have a big iron ball about the size of a bowling ball over here at 50 degrees Celsius, the big one has more heat content than the little one does. That's the major difference between the two. Temperature, I don't know of an equation that can make a direct conversion from kinetic energy to temperature, but temperature is proportional to the average kinetic energy. Let's make this K. Average kinetic energy of the molecules in any substance. It's a measure of kinetic energy. Although there's not an easy transition between the two values. Right? I can't say, if I know this one has so many joules kinetic energy, I can't say it has so many degrees temperature. How do we measure heat? The only way that I know the amount of heat content of some substance is to measure its transfer. And heat always moves from an area, could be in a substance, an area of high temperature to low temperature. It never moves the other direction. Always from high temperature to low temperature. That transfer of energy is measured as a change in temperature, and then we relate that change in temperature to the value of the heat content that moved. And we can judge what is the heat content of this object if we measure its move from here to here. So that's how they're related. All right, some more information. Definitions. This definition is derived from physics. All right, this is taking extra work. Do too. Yeah. I won't take time to wipe the board, but will dope my rag. There we go. And spread it. Okay. So let's define work. Work with I think we use a small w. Work equals a force applied through a distance. Right? I push on a box, it's laying on the floor, and it moves a certain distance, then I've expended work to do that. Okay. If I push on this board, I'm expending energy. Yeah, but it's not moving. So I haven't done any work. All right, so where did all that energy go? I converted it into heat. And sometimes if I hold it long enough, I can feel the warmth in my hands. If I push on it like that. So by definition, if it doesn't move, if you don't apply force or it doesn't move, then there's no work that's done. All right. Another concept now is state versus path. These are two types of functions. Y'all study functions in math class? Like f of x equals something? Yeah. Think of it that way. These are different types of functions. A state function as the path is irrelevant. Let's see, did I spell that right? Or is that an E? I don't even know if that was right. I think it's an A-V-E-N-T. Irrelevant. The path that we take in any measurement of a state function is irrelevant. All that matters is where did we start, where did we end. For instance, if I start in Charleston, which is what, about 500 or 600 feet above sea level, and I come to Beckley, which is about 2,500 feet, I've had to expend a certain amount of energy to get there, get to do that. And the amount of the energy that's the difference in my potential energy, put it that way, the difference in my potential energy from Charleston to here, it only depends upon a difference in position relative to the earth. I could go straight, I could go up the turnpike, or I could go up the old 2-lane roads. It doesn't matter. I've added to my potential energy a certain amount, and it only depends on the beginning and the end. Okay. That's why we say energy is a state function. All right. Okay, I left out one, I think. Yeah, it'll come up later. Work and heat are path functions. The path does matter. The easiest one to understand is work, right? If I'm pushing my vehicle up an incline to get there, but I also go this way to get where I'm going. It takes more work to go a greater distance to get there. So work is a path function. It does matter the route that you take. And heat. Heat is also. Now, the unit of measure, I think we introduced this at in the early part of the course. The standard SI unit for work is the joule, right? And it's derived from this force of 1 Newton times a meter. So a joule equals a Newton meter. And Newton is derived from Newton's second law of motion, which is force equals mass times acceleration. So this force is relative to that. So this Newton is equal to a meter, no, mass, excuse me, kilogram, standard kilogram, and acceleration is meters per second squared. So 1 Newton equals kilogram meters per second squared, and then 1 joule equals newtons times a meter. That's the only reason I show you that is so if you find yourself with an equation where you need to cancel units and you got a Newton and a joule and you got these others, maybe they won't cancel correctly, right? Until you put their equivalent value in there. Okay. So this is a definition of a state function. It only depends on where you are, not the route that you took to get there. Path function does matter, the route that you take to get from one point to another. Okay. So if we're going to measure the transfer of energy, which is really the only way you can deal, we don't have an understanding of energy or work or heat in absolute terms. So we measure a change from one state to another. And in order to do that, we have to define some conditions. We have to map out our space. Okay. So the first place we're going to map out is the system. Right. This is the system. And the system, sometimes you can arbitrarily say what the system is. It encompasses this, or sometimes the process determines what the system is. For instance, Bunsen burner. When the burner's going, the system is that flame where the mixture is and the chemical reaction is happening. Everything else is surroundings. Okay. See, this way now we can talk about crossing that boundary between the two. That's how we measure these quantities. First, we understand surroundings as the rest of the universe. But then we run into a practical problem. If you're going to measure the transfer from a system to surroundings or surroundings to systems, you got to know the whole universe to do it. If we don't know that. So we block off part of the universe. And we define the surroundings too. And rather than having to deal with the entire universe, we only deal with this part of the universe. Now, the universe is still out there, right? And if we're going to talk about what happens here, we've got to be sure that nothing crosses that boundary, right? So that's required, and there's some terms that go along with that too. So here are system and surroundings. And there's how we limit the extent of our surroundings. And we're going to talk about inside this box first, and then I'll talk about the box. So if we say that the system surroundings is open, then we can get a transfer either direction of both matter and energy. Yeah. That's open. So we define open. And sometimes that's the way we work a problem. But more often than not, we close the system so that only energy can exchange. So closed system says that can't happen. Only the energy can transfer. A lot of heat engines do it that way. And then the natural progression, if we do the same thing with energy, now we're saying that the system is isolated. Okay? And that's where we come to this boundary right here. This boundary says that everything that happens in here is isolated from the rest of the universe. That way we can coherently talk about these exchanges. All right. Now, let's see. I need to clean this up so we can talk about it a little bit. I'll rewrite that stuff in there. Okay, do this, that, and this. Let me do it like that. This is matter. And this is energy. And very often we're talking about energy, we actually mean heat. Especially with this definition. If we have closed the system so that there's no matter transfer, but energy can transfer, then we can say if heat flows into the system, right? Into the system, this is endothermic. Okay? Goes into. That means that the surroundings are losing energy and the system is gaining energy. If we say exothermic, right here, energy is leaving the system. Exo means out of. Endo means into. Exothermic means energy is transferring from the system to the surroundings, and we would sense an increase in temperature from that heat flow out. Whereas the endothermic, we'd sense a decrease in temperature. Right? Think of going to the hospital and you need an ice pack on a sprained ankle. They grab a certain pack, it's got water in it, and it's got a little capsule, and they break the capsule, mix it up, and it gets cold. You put it on your ankle and it feels better. Or you have a strained muscle, or you have a muscle cramp and you want to loosen it. They have another one, they break the capsule, mix it up, it gets hot. That's an exothermic reaction for the hot one, endothermic for the cold one. Excuse me. The energy lost by the surroundings has to be equal to the energy gained by the system, and vice versa. So, is the freezing of water an endothermic or an exothermic process? If we say water is freezing, what's it doing? It's going from a liquid to a solid, right? So our system is water, right? And if it goes from a liquid to a solid, what does that mean about the kinetic energy of the molecules, or the thermal potential energy of the molecules in the liquid versus the solid? If they're slowing down, they're losing that energy, aren't they? They have to slow down in order to form the solid, right? And we know that as happens with cold temperatures out. Instead of rain, we get snow. So in order to do this, we have to lose energy. Lose energy, go from liquid to solid. That's an exothermic process. The system will be whatever the water is, and the surroundings are like the air or whatever, in the refrigerator, freezer. Which way does the heat flow? That's an exothermic process. Okay, let's look at, I can leave that there. Let's look at these others. So I think I've got it animated, so I don't have to write it on the board. If the system is defined for us, we say in this case, your hand is the system. It gets cold when you touch ice. So if I touch ice, which way is the heat moving? It's out of the system, right? That's exothermic. If we look at the ice, it gets warmer when I touch it. Now we've changed, the ice now is the system. That should be the opposite, right? Heat moves into the ice to make it warmer. That's endothermic. How about water in a kettle that's being heated? We're adding energy to the water. Energy is going into the water, which is the system in this case. That's an endothermic process. How about water vapor condensing on a cold pipe? If the water vapor is the system, it goes from a warmer vapor to a colder liquid, then it has to give up energy. That's an exothermic process. And ice cream melts. It has to absorb energy. It's endothermic in order to be useless. Nobody wants to eat sloppy ice cream. Nobody I know of. So what we're trying to do with these slides is to develop an intuition for thermal transfer processes, because it's tempting to fall back to just popular understanding, which may be wrong. At least for the sciences, it would be. Okay, for each of the following, define a system and its surroundings and give the direction of energy transfer. For a chemical reaction, the balanced equation is the best means of defining the system. So when I talked about the Bunsen burner before, we had methane gas plus oxygen gas, and that would produce carbon dioxide gas plus water vapor. Okay, now that's not balanced, but that's what's happening. And that defines the chemical reaction after I balance it. Okay, so the system would be the collection of gas as it leaves the burner, and now it's reacting, right? So it gives up heat. That's exothermic. Okay. How about water drops sitting on your skin after swimming? It evaporates. How would you define the system there? Are you the system, or is the water the system? Well, actually, it could be either one. But if we define the water drops as the system, then they're extracting heat from my skin. It's endothermic process. As far as the water is concerned, Okay. All right, let's see, let me make some room here. I think we have the idea behind this one, so I can erase it too. Redraw it if I need it. Okay, that side of the rag doesn't have juice on it. There we go. Okay, hydrogen gas and oxygen gas react violently to form water. Right? You ever seen any old films of the space shuttle taking off? No? Okay. It's probably no surprise that my historical references become less and less relevant as I get older because my students are younger and younger. I never experienced it. We do still have some rockets that take off with liquid hydrogen and liquid oxygen as their fuels. The trend seems to be now they're going to methane and oxygen. They call it methylox. But anyway, hydrogen gas reacts with oxygen gas, and notice they're diatomic. You have to know that to make. Now, does it say we're making water vapor or liquid? Just says water. I'm saying it's hot enough that that's going to be a gas. Now let's go ahead and balance this. I need 2 oxygens here. That means 4 hydrogens. Now we're balanced. Okay. When we look at it in terms of where the energy is going, if this is the system and it's producing this product and it's generating energy that's leaving the system, it's exothermic, right? So if we were to put the energy term in here somehow, and I'm going to call it heat, and this is my term for heat, is enthalpy. Which side would it go on if it's exothermic? That'll go on the product side, shouldn't it? Yeah, it would go over here. That's where the energy is going to make it exothermic. Okay, now let's answer their question. Which is lower in energy, the hydrogen-oxygen mixture or water? Well, we can't create or destroy energy. So that energy came from somewhere. It had to come from here. So the energy content of the reactants is much higher than it is for the product water. Water's lower in energy. Okay. Now let's see, they're dragging us back toward thermodynamics, which is okay. It's the truth, even though we're not digging into it really deep right now. This first law of thermodynamics is still operating. Now we're going to define some more terms. Internal energy of a system. It's the sum of all the kinetic energy, all the potential energy of every particle in the system. That's internal energy. Right? We can say this is internal energy, right? Equals internal energy. Problem is, we can't measure it that way. It's an absolute value. We can only measure changes. So the change in internal energy for our system, right? This is our system. The change in internal energy is equal to both heat that we give a Q. Q is our abbreviation, small q for heat, plus work, right? Change in internal energy. So if Q is heat being added to the system, it's endothermic, then delta E will increase. If we do work on the system, then delta E will also increase. And if both of them are heat into the system, work on the system, then delta E will increase by whatever factor. Okay? The reason that we're introducing this concept now is because we're going to evaluate the effect of each one of these relative to gases first, because it's easier to describe gases relative to especially work. When we measure work on a gas, if the gas is the system, then we can identify the movement of a piston, say like this, under a given force, and it would move through a distance, right? So then we can equate that force moving through a distance is our work. Okay? And then we can measure the heat based upon the difference in temperature. The temperature here at this, right? There'll be an initial temperature here, and then once the piston makes it down to here, then there'll be a final temperature. And we can measure the difference in temperature and equate that to a certain amount of heat. Now, I'm getting there. I'll show you how to do that in a minute. Okay. We mentioned early on, when you make a measurement, you have a number and a unit of measure. But you also have a sign. Which direction is the number being applied? And since we have a difference in endothermic versus exothermic, we have to agree upon a sign for that also. So everything is defined in terms of the system. The sign reflects the system's point of view. So here's our system. If heat is moving into the system, that we're adding heat to the system, this value is positive. Okay? And vice versa. If heat is moving out of the system, then the value is negative. So values that have a positive value relative to the system, they are endothermic. And those that have a negative value are exothermic. So when we write a chemical reaction and we say the delta H, standing for enthalpy, is like 375 kilojoules per mole. If it's negative, then we know that that's an exothermic reaction. And that's where the signs can help you. Also, for W, the system is this gas in here. So the work that's being done, work equals force times distance. If the work is positive, then we are doing work on the system and we're moving down like that. So if we decrease the volume, that means the work would be positive, right? So in this example, W is positive. If we let the system do work on the surroundings by allowing the gas to expand, then the value would be negative because the system is doing work on its surroundings. Okay, it's like when your piston in your engine, you fire that gas air mixture and it drives the piston down. Now the system inside that piston is doing work on its surroundings so you can get from home to class on time. All right. Oh, Professor Dave wants to talk. Take it
Hey
away.
guys, it's Professor Dave. Let's talk about thermochemistry.
He knows a lot about the science stuff. Professor Dave explains.
Thermochemistry is the branch of thermodynamics that deals with the heat absorbed or produced by a chemical reaction. A reaction can either be exothermic, one that releases energy, or endothermic, one that absorbs energy. This change in energy is represented by delta H, or the change in enthalpy for the reaction. For our purposes, we can think of the change in enthalpy as being the change in energy for the reaction, or the energy stored in all the bonds of the products minus the energy stored in all the bonds of the reactants. If there is more energy in the products, delta H will be positive, meaning the additional energy had to be provided, making it an endothermic reaction. If there is less energy in the products, then that additional energy was released, making it an exothermic reaction. Energy, which is the capacity to do work, can have many forms, like mechanical, electrical, chemical, heat, and so forth. And besides quantum mechanical exceptions, energy is conserved. That means it can change forms, like heat energy that evolves when the chemical energy in a broken bond is released, but it won't be created or destroyed. Heat, represented by the letter Q, is a trickier thing to define, but a good way to put it is that heat is the energy that flows between a system and its surroundings due to a difference in temperature. Heat will always flow spontaneously from an area of high temperature to an area of low temperature. For a system, Q will be positive if heat is being absorbed by the system, and it will be negative if heat is being released by the system. When temperature and pressure are constant, Q equals delta H, the change in enthalpy. When we discuss thermochemistry, we will discuss energies in terms of joules or kilojoules. Another common unit used by chemists is the calorie, which is equal to 4.184 joules. 1 calorie is the amount of energy needed to raise the temperature of 1 gram of water by 1 degree Celsius. This is not to be confused with the food calorie, which is calorie with a capital C. This is actually equal to a kilocalorie, or 1,000 calories, also abbreviated as kcal. A thermochemical equation reports the change in enthalpy for a given reaction in stoichiometric terms. Here, the delta H listed is specific to the molar quantities given by the balanced equation. So if the number of moles of each substance as given were to react, the change in enthalpy would be as listed. To find the enthalpy change for a specific amount of material, just do some stoichiometry. If twice as many moles of material as are listed were to react, then the enthalpy change would also be twice as much as listed. Let's check comprehension. Thanks for watching, guys. Subscribe to my channel for more tutorials, and as always, feel free to email me, professordaveexplains@gmail.com.
Okay. Professor Dave introduced a couple of topics that we hadn't got to yet. So let's finish our discussion of work on the system and reference this diagram. Our terms are a force applied, right? What we generally, though, rather than absolute force, when we're talking about gases, we usually refer to pressure, like force per unit area. So that's why we also need a relationship between force and pressure based on the area of that piston. that's moving. The distance it's moved is here referenced as delta H, right? The change in height. And the change in volume then would be delta H times the area that it's moved, right? A cylinder volume is the area times the height. Right? So that's what we're mapping out that cylinder as a change in volume. Okay, so if we start with work equals force times distance, and then substitute some values in there, pressure equals force divided by area, force per unit area, and we solve for force, then we have pressure times area. We can substitute pressure times area for the F value in work. Okay, also, change in volume equals the distance that the piston moved times the area of the piston. And if we solve for distance moved, then we got force times distance, and we substitute change in volume divided by area into the D value. So this is what it looks like. P times A times delta V divided by A. A's cancel out. So the work done when a gas is compressed or when it expands, right, just change the sign, the work done is pressure times change in volume. Okay. So for an expanding gas, okay, here's the problem. For an expanding gas, the delta V is going to be positive. The change in volume is positive. It goes from a smaller volume to a larger volume. So the change is going to be positive. If we use that positive value for delta V and W, delta V and W must have opposite signs in order to stick with this convention. Right? So let's see. I'd put a, yeah, here we go. So if we allow pressure, this change in volume, so work is going to be pressure change in volume, then if the pressure is going to be constant, right? That's why we don't have a delta in here, because that pressure value is constant. But the volume will change. It will get bigger. So this is going to be a positive change. And this is just going to be whatever it is. The pressure is always positive anyway. So when that happens, that means that the system is doing work on its surroundings. That means W must be negative, right? W has to be negative to stick with this convention. That means we have to put a fudge factor in there. Stick a negative. So actually work is equal to minus P delta V. If we put values in here, atmospheres here, right? This is going to be liters. Then this is whatever we calculate as work is going to be liter atmospheres. Right? But how is liter atmospheres related to joules? Well, 1 liter atmosphere is equal to 101.3. This 1 equals 101.3 joules. There's our equivalence. And remember, anytime you have an equivalence between two units, you have a conversion factor. Okay, which of the following performs more work? A gas expanding against a pressure of 2 atmospheres from 1 liter to 4 liters. So if we do our calculation and it expands under 2 atmospheres pressure, right? And what's delta V? Well, it goes, the final is 4, and it's always final minus initial, so it's 4 minus 1, right? Right, the initial was 1, expanded to 4. So this is final, this is initial. So this is going to be 3 liters. So we have 6 liter atmosphere negative. That's A. How about if we are under 3 atmospheres pressure, right, negative 3 atmospheres, and then we expand from 1 to 3 liters. So 3 is the final minus 1. So that's 2 times 3 is minus 6 liter atmospheres. The same amount of work was performed by the system on its surroundings for both of them. I think of it in terms of internal combustion engines. If you have an engine with a long stroke but a tiny piston, you could theoretically get the same work with a big piston and a short stroke. Okay, let me make some room here. Let's see, what formulas have we come up with so far? We got change in internal energy, right, equals Q plus W. And then we have W equals force times distance. And it also is negative P delta V. And we'll keep our formulas over here. All right. Determine the sign of delta E for each of the following with the listed conditions. All right. So if we're going to have delta E, we're going to have conditions that reference Q and W. So in A, the first condition's an endothermic process. An endothermic process, which means Q is positive relative to the system that performs work on its surroundings, which is negative. Okay. Yeah. And then now we're talking about the values. If the absolute value of the work is greater than the heat, if this is greater than the heat, then delta E, yeah, if this one is greater than that one, then this value is going to be negative. I put them backwards. I put heat on the left. If heat is greater than work, right, if this one is greater than that one, then delta E is going to be positive. Negative, positive. Now, if we switch them around and do B and say that work is done on a gas and the process is exothermic. So work is done on the gas means work is positive. And Q, work is done on gas, is exothermic, it's negative. Okay, so if we have these two possibilities. Now, if work is greater than heat, then this is positive. So delta E then will be positive. And the other way around, if heat is greater than work, then our value would be negative for change in internal energy. Okay. There and there. All right. Here's another explanatory slide. What we're trying to do is draw a distinction between heat transfer and enthalpy. They are related, and under one condition, they're equal in value. But they are different values. Q is measured as the amount of heat transferred to or from a system during most processes that we study. Heat is actually a measured value of heat transfer. One of the two means of energy transfer, either then we're talking about work, or it's work is the other way to transfer energy. Let's see. Enthalpy, think of it as a potential, right? We don't have to measure it. We calculate it, actually. We calculate enthalpy, and that's the symbol is H, but we still have a delta H because we don't have absolute terms. This is a thermodynamic potential. It's like internal energy, but it's only related to heat. So that's where enthalpy and Q are second cousins. It's the potential heat energy of the system. Enthalpy is defined by the following equation, and there's another one. So enthalpy, which will be in units of joules, is equal to the internal energy of the system plus a change in pressure times volume. Okay. We don't have time to derive that equation, so take it on faith. So now what we're going to do is derive a situation, investigate a situation where the measured Q is equal to the enthalpy. So if we measure heat transfer in a chemical reaction, and we can relate that to the enthalpy of that reaction. Under one condition, we can do that. Professor Dave mentioned it, but now we're going to prove it. So we insert the equivalence of delta E into that equation. The delta enthalpy equals internal energy plus delta PV. So delta E we know is Q plus W, right? So Q plus W plus delta PV. If the process takes place at constant pressure, then we can pull the pressure term outside the delta because it doesn't change. All right. Now, if we look at the equivalence of work and pressure volume for a gas, we have W equals minus P times delta V. So we can substitute minus P times delta V for W. And if we do that, then we get a situation where the term P delta V minus cancels out the P delta V plus. So what that means is, if the pressure is constant in any chemical or physical process, then delta H equals Q. That's the only time that you can equate the two. Now, there's some cases where you can't help pressure changing. But most chemists will try, when they're investigating a chemical reaction, they will try to investigate it under conditions of constant pressure. That way, any heat transfer measurements that they make equal to Q are directly convertible into enthalpy values. All right. So we just finished with the combined gas law, right? P1V1T1 and then P2V2T2. So we have a system that's undergoing a process that will change each of those values. There are a host of different pathways that can be taken. From pressure 1 to pressure 2, from volume 1 to volume 2, from temperature 1 to temperature 2. that makes it a path function wherever those are involved to get from one state to the other. For that reason, measurements of heat transfer and work performed will differ depending on the path, because we've got equations for Q and W, and we know that they will not be the same if we substitute different values, especially for W. All right, we talked about that one extensively. But heat will also be that way also. I just used also twice. Okay. Whereas delta H is a state function, right? It's only interested in what we started at and where we finish. Initial states, final states. So up to this point, we have this is a state function. These are path functions. Let's see. Let's go down to this one. This is a state function. We already said this was state. And this must be state also. Yeah. Okay. The nice thing about enthalpy and its being a state function is that if we know the enthalpies that are associated with the reactants, in other words, formation of the reactants, and we know the enthalpies for the formation of the products, then all we have to do is subtract the reactants from the products, and we get the overall enthalpy of the reaction, regardless of the path. Doesn't matter what the path is. That's very useful. Oh, that's a good point. In that P1, V1, T1 up there, if P1 to P2 changes, then our house of cards falls apart. Delta H then would be different from Q. Okay. Let's see. Enthalpy is a state function. Delta H equals Q at constant pressure. Yes. Delta H equals H products minus H reactants. Delta H equals H products minus H reactants. I'm pretty sure what they're saying here is that the value that we associate with delta is H for products is the delta H of formation for those, the delta H of formation. We have to define what we mean by that. And we'll get to it eventually. But let's talk about a real world reaction, propane, C3H8, that's propane. And we combine it with oxygen and cook steak with it. Or we cook on the stove. If your house is equipped with propane only, then we may dry our clothes with it also, or heat the house with propane. This is the reaction. And it produces a whopping amount of heat, right? 2,221 kilojoules per mole of propane. When we look at that equation, sometimes they don't even put the moles in there. But since we did define it as moles of propane, we see that moles of propane in this reaction, the coefficient is 1. So that's valid. But what Professor Dave was trying to say was when we say delta H equals negative 2221 kilojoules, if it's associated, it has to be associated with a balanced equation, then this many kilojoules for that reaction, this many kilojoules will be generated if 5 moles of oxygen react with propane, or if 3 moles of CO2 react with as a product and 4 moles of water are produced. So we could say this, per mole of C3H8 or per 5 moles of oxygen or per 3 moles of CO2 produced or per 4 moles of water produced. That value could be associated with any one of these if we're referencing that particular balanced reaction. Now, let's take the problem that they're working with here. C3H8 plus 5O2 yields 3 CO2 plus 4 water. Okay. We've done some stoichiometry, haven't we? We did that for the second exam. We sure did. Yeah. Okay. So assume that all the heat comes from the combustion of propane. Calculate delta H in which 5 grams of propane is burned in excess oxygen. That's good. We're told that this is excess, and that makes sense. And we have 5 grams here, right? We can't relate this to the enthalpy because this is in mass, and that's related to the moles. So this has to be converted to mole, right? 5 grams of propane. We need a conversion factor that'll go from grams to moles, right? We know what that is. Molar mass of C3H8. So we have 3 times 12.01, and we have 8 times 1.01. So this is 36.03. This is 8.08. And that's there. And that's right, for 44.11. Divided into 5. And that's 0.11335 moles of propane. So now we can use the enthalpy, which is in terms of minus 2221 kilojoules per mole of propane. Right, 2221. And that's negative 2.5. Let's see. All right, we only have 3 significant figures. Sorry, 3 significant figures. So this is 2 times 10 squared kilojoules. That's the absolute amount of heat produced from this amount of propane being burned in excess oxygen. Oh, they've got it in standard notation. Take these two, move them over like that, minus 252 kilojoules. There you go. Okay. Calorimetry. So you remember Professor Dave was talking about the calorie. Calorie, I think, is Latin for heat. Anybody had any EMT training? Okay. What do you look for when someone has experienced an injury or disease? There are 4 things. There's calor, right? You can feel warmth from an infection or an injury. There's dolor, which is pain. There's, let's see, calor, dolor, rubor. It's red colored. Let's see, calor, dolor, rubor, and there's one other one. I always forget the fourth one. But calor is one of them. You feel heat from the wound. So calorimetry, metry means to measure. So we're going to measure heat. And that's what we're going to do eventually when we get to the lab on calorimetry. Things got pushed way back, so we're not going to get to calorimetry for another month. Yeah. That's okay. We just have to go back and review some formulas. So how do we measure heat? Well, we define some terms. Heat capacity. Heat capacity is equal to the heat absorbed or evolved from an object with a given delta T. So it can either absorb heat or evolve heat with a change in temperature. And it depends on whether it, if it absorbs heat, it's going to get hotter. If it evolves heat, it's going to get colder. That's heat capacity. And this is an extensive property. This number of joules, this heat capacity, this joules, will change depending on the size of the object for any given change in temperature. Okay? Specific heat capacity takes this value and it divides that value, this heat capacity, divides that value by either mass or moles. So it's ratioed to the mass of the object or ratioed to the moles of the object, and that makes it an intensive property. Since we're basing it upon this unit of mass or moles, then if we make it bigger, it's still relative to the unit of mass or moles. That makes it an intensive property. And this is the one that we're typically going to use in calculations, specific heat capacity. And it has units of measure of energy, joules, per, in this case, per gram degree, gram degree C. For this one, it would be joules per mole degree C. You can see it both ways. Oh, and this is usually called molar heat capacity. Molar heat capacity. All right. So think of it, let's do a thought problem. Einstein was famous for those. You just sit and think about stuff. Create these imaginary problems and then solve them in his head. Well, on paper eventually. If two reactants in solution at the same temperature are mixed and the resulting solution gets warmer, this means the reaction taking place is exothermic. It gives up energy from the system. Right? An endothermic reaction would be one in which it gets colder. And we talked about the hot and the cold packs earlier. Oh, how long are you going to take with this, Dave? 4 minutes? Okay. We got time, I think.
Hey, it's Professor Dave. Let's talk about calorimetry.
He knows a lot about the science stuff. Professor Dave explains.
Different substances absorb heat at different rates due to various structural factors. The heat capacity of a substance is the amount of energy required to raise the temperature of that sample by 1 degree Celsius. A variation of this that is more useful for calculations is the specific heat of a substance, which is the energy required to raise 1 gram of a substance by 1 degree Celsius. Heat, temperature, and heat capacity are all related by the following equations. The amount of heat exchanged in a reaction is equal to the heat capacity of the substance times the change in temperature for that substance. Or, more practically, the heat exchanged is equal to the specific heat of the substance times the grams of the substance present times the change in temperature. We can use this information to learn about heat transfer using a process called calorimetry. For those of you in an introductory chemistry course, you'll probably do some variation of a coffee cup calorimeter experiment. Let's look at how those work. A coffee cup is a pretty good insulator. That's why we use it for coffee, so that the heat doesn't escape so quickly and the coffee stays hot for longer. This makes it possible to take pretty reasonable data about the temperature change in a cup of water when we add a hot piece of metal. We can measure the temperature change in the water and use that information to calculate the specific heat of the metal. So, let's say you heat up a metal by placing it in boiling water at a known temperature until it is just as hot as the water. Then, with tongs, you place it in a coffee cup containing a known volume of room temperature water with a thermometer. The water in the cup will heat up slightly as the heat from the metal flows into the water, and we can record the resulting temperature change. From there, we just do some math. We use the specific heat equation and plug in the data for the water. The temperature change is what you recorded. The mass of water in grams is equal to the number of milliliters of water. And the specific heat of water is a known value. This allows us to calculate the heat absorbed by the water. Well, the heat absorbed by the water was the heat released by the metal. So we can take that same quantity of heat and plug it into a new equation for the metal. That value goes there. We weighed the metal beforehand, and this time the temperature change of the metal is from the boiling water to the final temperature in the coffee cup. So you can solve for the specific heat of the metal. This is useful for identifying unknown metals if you are given a few different specific heats and asked to decipher which metal you are given. Let's check comprehension. Thanks for watching, guys. Subscribe to my channel for more tutorials, and as always, feel free to email me, ProfessorDaveExplains@gmail.com.
I got a pause built in if we run out of time. Okay. Now, the way Professor Dave explained it, doing that calorimetry, the calculation part, the coffee cup is the same, right? I used coffee cups. They weren't as efficient back then. Now they're made out of styrofoam, and you stack a couple of them together and you got a perfect calorimeter. Let's see. Yeah, I got the equations there. I can erase this. So when you have that coffee cup calorimeter, and we usually use a double coffee cup, and you'll have a lid with a hole in it. This one has a stir in it, and I used to use a stir in the lab, but the material it's made of can't stand up to certain reactions. So I don't even use a stir anymore. Just a coffee cup and a thermometer. Okay, there's your thermometer. And if you're careful, you can use the thermometer to stir your material. Okay. The first point I want to make about this calorimeter is this is the system. Okay. Everything else is surroundings. And this system is isolated. That is, we don't care about the surroundings. Because the system is isolated, then whatever happens in Vegas stays in Vegas. Whatever heat change takes place in here, we know that anything that adds heat or subtracts heat stays inside, and the total has to be equal to 0. That's the first thing to remember. And all we have to do now is say, all right, I've got this process going on, and I've also got this process going on, and I've got this process going on. And it can go on forever. Those three heat terms added together must be 0. Okay. Now, as it turns out, the calorimeter itself enters in, it's part of the system. So its heat can change. The thermometer can change temperature as it absorbs some heat from the system. Even the styrofoam can absorb a little bit, or the lid. So we usually have a term in here for the calorimeter. Right? Then we have 2 or 3 other terms depending on what you're trying to measure. Right? Say we have heat of the reaction. And then we're conducting the reaction in aqueous solution. We have a heat change for the water. For example, all of those must be equal to 0. That way, you don't get confused by saying, well, I'm calculating this heat amount and this heat amount. Which one goes where? Right? If you set it up this way, then the math takes care of itself. All right. Isolated system. Heat can't transfer. It can enter the walls of the container, but it doesn't go outside the container. All right. So here's our equation. Q equals specific heat times the mass of the substance or the object times the change in its temperature. All right. And if we look at the values where Q equals SM and change in temperature, this is going to be in specific heat is going to be joules per gram degree C. Mass is going to be in grams. Change in temperature is going to be degrees C. And this is going to be joules. So look, numerator, numerator, denominator, denominator, those cancel, leaves us with joules. So our equation is valid. And we don't have to change the temperature to Kelvin to do this. You can, right? Because the degree for Kelvin is the same as the degree for Celsius. So if you're given Kelvin degrees, you don't even have to change them. You just put the Kelvins in before and after. All right. There we go. There we go. And so let's do some little intuitive problem here. If you have a 100-gram sample of water in here, at 100 grams, of water. And the water is at 90 degrees. Oh, this 100 grams of water is at 10 degrees. Okay. And we have another container over here with water, 100 grams at 90 degrees, right? Okay. And let's say this is a bigger cup than it looks like, so we can add all that water to it. If they're the same mass, each one, and we put them together, like we add them together, where is the temperature going to end up? They both have the same heat capacity, right? So they're gonna change temperature with the same amount of heat each way. So if this one's at 10 and that one's at 90, they're gonna meet in the middle, aren't they? Somewhere, right? If they're the same mass, then they should meet in the middle between 10 and 90. Right? So this one would go maybe, if this one went plus 40 degrees and this one went minus 40 degrees, they meet in the middle at 50 degrees. Okay. That was the easy one. This one's not so easy, but it's still intuitive. Let's say now we have 100 grams at 90 degrees here, like that. Okay. And this one is 500 grams. So which one has potentially more heat than the other? Heat capacity, not specific heat capacity, but total heat capacity. This one, right? Because it has more mass. So where should this one end up? We could calculate the exact value, but we're looking, this is intuitive. So the temperature should be closer to 10 than it is to 90, shouldn't it? Because we've got more mass here. So it's between, it's not 50 because they're not equal. So it's between 10 to 50 degrees. See, is where it should end up. I think, actually, I think we're going to calculate that. Okay, calculate the final temperature. Good, I worked it out. All right, for this problem, we're going to ignore the heat capacity of the calorimeter. Okay. We haven't got to the point where we know how to determine that value. The value is going to change depending on, well, the uniformity of manufacture of styrofoam and of the thermometer and of the lid are not good enough for us to say, if we have 2 cups, a lid, and a thermometer, we know exactly it has this heat capacity. We can't do that. So you have to measure it. You have to determine it. And then you keep all those parts together because that's your calorimeter. And if you change a part, you change the heat capacity. Okay, so for this, we're going to ignore. So there's going to be a heat term for the cold and a heat term for the hot. Okay. So the heat term for the hot is SM delta T. It's a different delta. Yeah, it's a different delta T. Excuse me. I was thinking for a minute. Than it is for the delta T for the cold. The heat capacity is the same, 4.184. So that's the same. The masses are different, right? So we put the mass here for the cold, mass here for the hot. Now, here's where the calculation of the temperature differs. For the hot, the change in temperature equals final minus initial. What is the final temperature? It's unknown. That's the question. What's the final temperature? Right? Minus the initial temperature, 90 degrees. Okay. So that term substitutes for delta T for the hot. Right? That first term. The final temperature for this one is going to be the same as that one. So this delta T equals final minus initial. And it's going to be final temperature. Oops. Final temperature minus 10 degrees C. Okay, so that's why we plug that value into the 500 gram term. Okay, now all we have to do, since we have both of those set to 0, we have only one unknown and we can solve it. So we start parsing out the values. Right? 418.4 is the product of 4.184 times 100, and then T minus let's see. Let me do that. You want me to do that on the board instead of just flashing up the, or do you care? I mean, are you following it?
Yeah.
Oh, okay, then I won't waste your time. What we've done is we've taken the first one, which is the hot, the 100 gram, and we're working our way down through the calculations to where we can get the TF on one side and numbers on the other side, and that'll answer our question. So what we end up with is this ratio here, and solve for TF, we divide 58,000 by 2,500. And that gives us a 23 degrees. And that's between 10 and 50. So the actual temperature is less than 50. In fact, it is 23 degrees Celsius. Okay. Now, if we change conditions so that we have 50 grams of water, we'll take one of those zeros out. 50 grams of water. And now what are we going to put in it? We're going to put in at 10 degrees. Okay, we're still there. And we're going to put in an iron ball that weighs 50 grams and it's been heated to 90 degrees. All right. So we have two heat capacities, specific heat capacities, one for the water, one for the iron. So our terms then, once we put the terms into the equation, 0 equals Q for the water, Q for the iron, then we want to say, all right, where's the temperature going to be? Calculate the final temperature of the water. Well, the water has a higher heat capacity, which means what? Higher specific heat capacity means for the same mass, the temperature changes less for a given amount of heat in a higher heat capacity. So the temperature change for the metal at 90 degrees should be a lot more. Its delta T should be greater than the delta T for water. So it ought to end up also at between 10 and 50. Okay, come on. There we go. So here we have our term for Q for the water and Q for the iron. And again, we're ignoring the calorimeter for now. So the difference is now that the S for the iron is going to be different than the S for the water. All right? By a factor of about 10 times. Heat capacity for iron is much, much lower than water. Anybody got an idea why? Water is a polar molecule. It's slightly positive here and slightly negative on this side. Not complete charges, right? Just slightly. And it associates like this. With all those water molecules, this is a very strong intermolecular bond. And it takes a lot more energy to move those molecules apart. So it can absorb a lot of energy with only a very slight change in temperature. Whereas iron is just like a collection of iron atoms. And they're attracted by, well, one model says electron C and the other says molecular orbital. We'll get there eventually. So we're just reducing the equation. Again, solving for that final temperature. And if we do our math correctly, we should end up with 18 degrees. So the metal, let's see, the metal was 50-gram ball, 50 grams of water. Okay, so we have equal masses of the two, just like we had equal masses of water before. But the temperature stays closer to 10 than it did with the water of equal mass at the same temperature. The hot water was 90 degrees, the iron ball is 90 degrees. So that tells us that that it's all due to that difference in specific heat capacity. Okay, let's see, we're 4 to 3. I'm trying to see if I think I've got time enough. We got 3:50. You know, maybe we can finish this. If we finish this lecture, then we can spend more time on the review next Thursday. Let me see if I can do that. I think I can. Then I can post the whole video together also. Let's see. Yeah, I think so. We're not that far from the end. Okay. All right, those are examples of calorimetry. When we get to the lab, I've got more extensive descriptions of how the math operates and how to determine the C, the big C, not the little s, the big C for your calorimeter, because you'll have to know that when you do the lab. So that's the first step. You determine the calorimeter constant, then we do the 3 experiments. Okay, Hess's law. Hess's law is very simple. It simply says that since enthalpy is a state function, if we have an equation here for a reaction, and we don't know what the enthalpy is, it's an unknown enthalpy. Right? Then if we also have other equations, 3 or 4 or more, it doesn't matter how many, and we know the enthalpies for each of those equations, then we can combine those equations as long as they give us the target equation. Then we can also combine their heats to give us the enthalpy for the new equation, the new reaction. That one advantage here is it doesn't mean that we have to conduct the laboratory experiment with that new reaction. We don't have to do it unless we really want to. That's the first meaning. Second meaning is sometimes these new reactions, we don't know how reactive they are. Right? If we put too much together, then we might have an explosion in our lab and destroy things. So if you can calculate the expected enthalpy for your reaction before you actually do it, then you can either say, I don't want to do that reaction, or you can say, if I use a very, very, very tiny amount, then I can secure the area and it'll be safe. Oh, Dave's going to talk again. Hess's law. Oops. Come on, Dave. No, that's not what I wanted.
Professor Dave here. I want to tell you about Hess's law.
He knows a lot about the science stuff. Professor Dave explains.
Thermochemical equations can be manipulated to give important data about chemical reactions. We can use them to predict exactly how much energy will be absorbed or released by a reaction, which is very important because we don't want any unexpected explosions. There are two ways we can use tabulated thermochemical data to calculate the delta H of any reaction. The first way requires that we manipulate thermochemical equations in specific ways. So let's be aware of some rules. First, if a reaction has a particular delta H, the reverse of the reaction will have the opposite delta H or the same number with reversed sign. Second, if molar quantities in the equation are multiplied by a coefficient, so is the delta H. So if you double all the substances, double the delta H. These are things we can do to thermochemical data to be able to add equations together to result in a reaction we are curious about. Here's what I mean. Let's say we want to know about the change in enthalpy associated with a reaction, like this one. But it is difficult to measure experimentally. We can take other reactions with known enthalpy changes and rearrange them to align with our equation and get the data we want. The first reaction provided has carbon graphite on the left, which is where we want it. But the equation we want has 2 moles of graphite, so let's double this one. We get 2 moles of everything instead of 1, and we double the delta H. Next, this other one has CO on the right, where we want it, and in the right amount. So all we need to do is add these equations together. The O2 and CO2 will cancel because they are present in the same amounts on both sides, and we are left with the substances in our original equation. Since we added the equations, we also add the delta H's to get the delta H for our equation. This kind of manipulation is allowed by Hess's law. We can manipulate the coefficients of a reaction or reverse its direction in any way necessary as long as we change the delta H associated with it in the appropriate way. Then we add or subtract the equations as necessary to give us precisely the equation in question. The delta H you get by doing the arithmetic will be the delta H for the reaction. Another way to calculate an unknown delta H is to use standard enthalpies of formation. This is denoted by the following symbol, and it represents the enthalpy associated with forming 1 mole of a substance from its respective elements in their standard and most stable state. Most stable state means the most common allotrope, or physical form of an element. So carbon graphite instead of diamond, diatomic oxygen instead of ozone, and so forth. Standard state just refers to standard temperature and pressure, which is room temperature and atmospheric pressure at sea level. That's what is meant by the degree symbol. We can calculate the change in enthalpy for a reaction by adding up the standard heats of formation of the products and then subtracting the sum of the standard heats of formation of the reactants. The heats of formation can be found in your textbook or online, and you just plug them in, multiplying each value by the coefficients in the balanced equation. Let's check comprehension. Thanks for watching, guys. Subscribe to my channel for more tutorials, and as always, feel free to email me, ProfessorDaveExplains@gmail.com.
Professor Dave for today. He mentioned calculating the enthalpy for a reaction based upon the heats of formation, the enthalpies of formation for the each of the reactants. And we're going to get to that. This reaction that we see here, nitrogen plus oxygen yields 2 NO2s, can be carried out in two distinct steps with the enthalpies as shown. Right, so we can get N2 plus O2, 1 O2 to get 2 NO. And then we can say 2 NOs plus O2 yields 2 NO2. And the enthalpies there on the right. So the first step is endothermic and the second step is exothermic. But if we, and the first condition for using these types of equations is when you add them up, they must equal the target equation. No exceptions. So if we cancel those, right, and we add them together, we do get N2, 2O2, and 2NO2. And then we can add the enthalpies together and get 68 kilojoules. This is just a diagrammatic way of looking at it. And the reason we can do it this way is because enthalpy is a state function. So you can either, on the left-hand side, you can either go all the way from the bottom to the top and then come down with the second reaction. So the first reaction takes us up, it's endothermic, brings us back down to our target, or you can go straight from reactants to products with the red. And then the one on the one on the right is an expression of that one. Okay, these are the rules, and Professor Dave mentioned them. If a reaction is reversed, if you have to flip the reaction, then you change the sign on your delta H. If you have to multiply by a constant value, you multiply that times the delta H also before you add it together with the rest of them. Okay, so if we consider the following data, ammonia yields half N2 and 3/2 H2. Notice that we're introducing fractional coefficients now. We started off with only whole numbers. This is fractional, right? We have to do it that way. Then 2H2 plus O2 yields 2 waters. And if we use them to calculate the delta H for the bottom reaction, where 2 nitrogens plus 6 waters yields oxygen plus ammonia, then what we have to do is, and the best way to work these types of equations is to work backwards from the target equation. Right? And those are just simple instructions. So if we reverse the two reactions, now we get ammonia on the right-hand side for the top reaction, which is where it needs to be. And we get water on the left-hand side where it needs to be. And we've modified the signs to take advantage of that. Then we need to multiply by constants. Right? We need two N2s. So how would you get 2 N2s from a half N2? Multiply by 4. Right? So that's what we're going to do first. Multiply by 4 to the first equation. And then the second equation, multiply by 3. And that's what we get. And if we cancel common terms, if you have the same number of species on the left and the right, they cancel. And then we add them together and we get 1268 kilojoules for that reaction. And we didn't have to do the reaction. Standard enthalpies of formation. All right. By definition, a standard enthalpy of formation starts with the product. So if we have water on this side under standard temperature and pressure, which for everything else except gas equations is 25 degrees Celsius and 1 atmosphere pressure. This will be a liquid. Okay? You start with 1 mole of the product, the formation of the compound. And then we go back and say, all right, we need hydrogen in its most stable form. That's a gas. And oxygen in its most stable form, that's a diatomic gas also. Now, to balance the equation, we don't touch this side at all. We go to this side and say, if we need 2 hydrogens, we've already got them. We leave that one alone. This side, we only need 1 oxygen, so the coefficient has to be 1/2. That's how you write a standard equation for the formation of a compound. For a gas, the pressure is 1. If we have solutions involved, it's 1 molar concentration. Pure substances would be like liquids and solids, like this is a liquid, solid. For an element at 1 atmosphere and 25 degrees, okay, it's coming. I don't like this. Let's skip that. That's too confusing. Yeah. We already covered that topic from a previous slide. Okay, let's see. Okay, so once we have the standard heats of formation for each of our reactants and products for a given equation, then all we have to do is add them up for the products and subtract for the reactants. Now, the standard heat of formation for this is a value, right? The standard for elements in their standard most stable state is always 0. Right? So if you have elements in an equation, then their delta H's are 0. So here we have 2 sodiums plus 2 waters, standard states yields 2 sodium hydroxide in aqueous solution, which must be 1 molar, right? And H2 gas. Sodium and hydrogen have standard heats of formation of 0. So all we have to do is say products, 2 times sodium hydroxide. What's sodium hydroxide? Minus 470. Oops, left out a 7. 470 kilojoules per mole, and this is 2 moles, right? And then we subtract the water minus how many waters? We have 2 waters. So 2 moles of water, and the standard heat of formation of water is minus 286. That's 286 kilojoules per mole. Okay? So 2 times this one would be what? 940 minus 940 kilojoules, because the moles cancel. And this one would be 12, 16, 17, 572. But that's a minus and that's a minus, so this is a plus. Okay? So I like to do it by hand sometimes just to keep my brain active. 13.6, 85, that's 3. This is a minus 368 kilojoules for that, for that reaction. Okay? Really simple. And thousands of these reactions have been tested against this procedure. We've determined the heats of formation for all these compounds, and then we actually go to multiple reactions and measure the enthalpies for them, and they come out spot on every time. So there's plenty of experimental evidence for the validity of this procedure. All right. So let's see. Yeah, we're coming down to the end. I get to get up on my soapbox now. And harangue the panicked environmentalists. Okay, what sources of energy do we have available to us? Well, fossil fuels, obviously. What do we mean by a fossil fuel? What's a fossil? It's something in the ground that's been preserved, right? So the fuels have been preserved in the ground. Oil, natural gas, coal. Those are the three biggies. There are some, I guess you can consider peat a fossil fuel. It's just not very far along in its formation. They use it in Scotland and Ireland to make whiskey. They claim it makes better whiskey. I don't know about that. So those are the major fossil fuels. For the longest time, right, before the discovery of, actually coal came first. For the discovery of coal to drive the Industrial Revolution, wood was used. And when pure carbon was needed for the formation of steel, they took wood and they pyrolyzed it. They stacked it in these kilns and sealed it off so no oxygen could get to it. And it just broke down the compounds into pure carbon. And that was used, that was called coking. And the procedure was modified and used also. Once we found coal, we do the same thing to coal. And we coke coal to make pure carbon, and that's what goes into the steel making process. But wood was it for the longest time, and that's why a lot of forests that used to be aren't anymore. Because the energy density of coal, oil, natural gas is much higher than it is for biomass, like wood and other things. Hydroelectric, right? I grew up, I was a kid in Tennessee. So one of our favorite things was to go to various dams that were on the Tennessee River when back in the early 20th century, when rural electrification was the watchword. And one of the ways that we were electrifying the rural communities was if there was a river with enough slope in it, you just throw a dam in there and make electricity from the flowing water. And there are lots of them on the Tennessee River. The Tennessee River runs through Tennessee like kind of like this. Then it hits the Ohio River. So you've got a lot of places in here where you can dam it up, make electricity. And we go to those various ones that were close. I lived on this end of the state, so we focused on that end. Hydroelectric. The problem with hydroelectric is for large demand electricity, all in this, at least in this country, all of the available water sources for producing that much electricity have been used up. Right, there are no more. There are some that you could do for small projects like one house or 10 houses, or even some of them up to 100 houses, but not 10,000 houses or a full city worth. You know, that takes a Hoover Dam to do that. That's how Las Vegas gets its electricity, from Hoover Dam. Nuclear power. That's my favorite. We have enough coal in the ground, they think, our reserves, to last us another, say, 300 years, maybe 250. You know, we've got enough fissionable material in the ground to last us for the next 700 or 800 years. And there's a lot of work being done on modular nuclear reactors. So you don't have to build these huge monstrosities with the big domes on them and run the risk of a China syndrome. You make them in small modular units, and then they can even be portable. Like this community needs a little bit extra. Say the Olympics are coming to town. They need extra power. They just ship in 2 or 3 of these modular units, generate all the power they need, and when the Olympics shut down, they go out somewhere else. A lot of them are floated on barges, and they tie them into the grid, local grid. Nuclear power, actually, there have only been a handful of nuclear accidents. Now, the problem with nuclear accidents is they can be devastating, right? The one that happened in Japan, Fukushima, I think it was the name of the reactor. That was kind of foolish, building a reactor like that without special safeguards next to a major fault line, right? Japan, you know how the ring of fire goes around the Pacific, right? A lot of tectonic activity from the US side all the way over through Alaska and back down through the Russian Kamchatka Peninsula and Japan, and then down into the Philippine area. All of that is tectonically active. You produce volcanoes, you produce sub-ocean shifts that can produce tsunamis. And that's what happened with that Japanese reactor. They had a huge displacement offshore, several miles offshore, and it created a massive tsunami that came in and just dumped on that reactor. And it lost some of its fissionable material, was dispensed into the surrounding environment. They've been cleaning it up ever since. So there need to be extra precautions taken, obviously. But if you make these smaller modular reactors, then the consequences of an accident with one of those is much less devastating. And there are various types of, years ago, the United States, for some reason, probably political, decided to go with pressurized water as the heat transfer medium for the reactor. So they pressurized this water, be under massive amounts of pressure at high temperature, right? It has to be under high pressure to keep it from vaporizing in the pipes. So if it's under very high pressure, then you can heat it up to several hundred degrees, right? And transfer a lot of energy in it. But if it springs a leak, right, or if you have a scram of some kind and a valve breaks, something like that, then under that pressure and with that heat, that water is going to instantly vaporize. So that's why the reactors that you see now, the older reactors, have this big concrete dome. The reactor sits way down here. That dome is to contain the vapor from a leak. If it leaks, it's going to vaporize. The rule of thumb is a liquid will expand to a gas about a ratio of 1,000 to 1, volume for volume. So this thing has to be 1,000 times bigger than all the water that's flowing through that reactor. Okay. But there are other designs that got passed over when this pressurized water system was adopted by the US. And other countries have done lots of research on it and used different ones. Now, Russia, they really screwed up bad with Chernobyl. Their reactor design over there was essentially the same design that was used at the University of Chicago for the first controlled reaction by Enrico Fermi. They just stacked bricks and had little radioactive things in there, and they had a place where they could put moderator rods into it. But it was just, that's why they call it a nuclear pile, because they pile bricks. And Russia followed that pattern in Chernobyl. And through a series of human errors, compounded by poor technology, they had a massive problem and they scattered radioactivity all over Europe. And then we made a nice movie out of it, right? We, what was it? Matthew Broderick was a scientist working on worms that had mutated because of that. And they sent him to the Pacific and then to New York City to fight Godzilla. Okay. Wind and solar. Wind and solar do not contribute a significant portion of the power that we need. For one main reason, they're intermittent. Solar is predictable, reasonably predictable, right? During daylight hours, you've got power. When it turns night, you don't have power. Wind is less predictable. There are some places on the earth that are fairly constant in the wind flow, and the local application of wind turbines is useful. It works. But what you need is a way to store massive amounts of energy for uses when they're not producing. Okay? And that means battery technology. And there's been some advances in battery technology, but it's still nowhere near what's needed for large-scale distribution for the grid. Let's see. I'll talk about some other things that are wrong with the environmentalist pet projects. This just shows you that our reliance on energy has shifted over time. In the mid to late 19th century, it was all wood. Then we shifted over to coal, and then gradually petroleum and natural gas have taken over that. And coal has been more of a, it's still used in some places for energy production, but largely coal is an industrial ingredient, most often used for steel production. Okay. When environmentalists get their panties in a knot, they usually talk about the Earth's atmosphere and how we're polluting it, right? And they've been for the last, I don't know, 50 years or so, they've been pushing this idea of man-caused global climate change. At first, it was global warming because that sounded worse. Now, and since the Earth started cooling off, they had to change their tune to global climate change. But they're still blaming it on humans, right? And they're saying that because humans, during the Industrial Revolution, we started pumping out lots of CO2, right? And they blame CO2 for causing the greenhouse effect, right? Right, there are a number of arguments against that. One is that CO2 is not a very efficient trap for energy. Let's see, I think I've got a slide on the next page. Yeah, this is the idea. Radiation from the sun comes in and strikes the earth, and it's all these mixtures of wavelengths, and then some of it is re-radiated as longer wavelengths, like infrared. And infrared is preferentially absorbed by certain molecules in the Earth's atmosphere, right? CO2, it does do that, right? I used to have a chemical analyzer where we analyzed carbon by changing it to CO2 and then measuring its concentration with a spectrophotometer that used infrared radiation. So it's true, it does absorb infrared. Water also absorbs infrared. It's less efficient than carbon dioxide. They're both less efficient than methane. But the difference is between intensive and extensive properties. You have orders of magnitude more water in the atmosphere than you do CO2. So the water has a much, much greater effect on blanketing the earth and holding in warmth than does CO2. Now, there are other reasons to keep the atmosphere clean. right? Not just global warming. Global warming puts money in the wrong pockets. Let me put it that way. But if we want to protect our health, then we want to watch what we do spew into the atmosphere, especially on a local scale, right? In California, where they have this atmospheric inversion problem, in cities like Los Angeles, at certain times of the year, the cold air rides in over the top of the hot air and keeps it bottled up. And they just keep driving their cars and spewing out pollutants, and you get smog, which is a patmento. I think there's a word for it. It's a contraction. Smoke and fog, smog. Okay, so let's see. Did I leave anything behind here? Okay. Now there are places in the solar system, one in particular that we know of, where the greenhouse effect is run away. That's Venus. But Venus has massive amounts of carbon dioxide and sulfur dioxide, sulfuric acid, in its atmosphere, which makes it a very efficient trap for heat. And Venus is still volcanic too. So it's producing a lot of heat from inside. It's closer to the sun. It's getting heat from the outside. And that blanket of CO2, which is thousands of times more concentrated than we have, it does produce a greenhouse effect. That's probably where they got the idea. Okay. New energy sources. All right. We can convert coal to natural gas. It produces a waste product, but we're finding ways to use the waste products. And a natural gas or methane is much less polluting than coal is. Hydrogen, that's the holy grail of fuel. If we could produce hydrogen, we'd have a cheap source of fuel. We need a cheap source of energy. That's where nuclear comes in, to split water into hydrogen and oxygen. We can either keep the oxygen or send it back in the atmosphere and keep the hydrogen, and that becomes our fuel, right? We can run it. There are some engines now, internal combustion engines, that have been modified by some car companies to run on hydrogen. Right? It's less efficient, right? But it's non-polluting, because the product is just water, right? Hydrogen and oxygen make water again. Energy alternatives, right? Oil shale, which is obtained by fracking, right? Shale is very dense rock. It has oil in it, but it's hard to get it out. So this procedure called fracking, this amazes me. You've got a layer here of shale that's got oil in it, and you've got the level up here, and you've got your drill derrick here, and they go down, and they can actually put something in the bottom of the hole that makes it go like that, make a right turn, and they send this pipe out through that stratum of rock, and then they pump a special kind of drill mud down that hole, and under enormous pressure, thousands of psi, first they send a shot tube down there with like these shotgun shells, and they poke holes through the pipe. Then they send the fluid down there, and under that enormous pressure, it cracks the rock, and that gives a pathway for the oil or the natural gas to come back out. They do this with wells that have been pumped out, they say, right? They pumped all they can under normal conditions. So they go down and they do this thing to it, and they essentially clean it out of the oil that was left behind. Natural gas also through fracking. Ethanol, The problem with ethanol is the amount of energy it takes to produce a gallon of ethanol is more than you get back when you burn ethanol. It's energy, actually it's a negative energy, it's a net sink for energy. And the production of ethanol would not continue if it were not subsidized by the government. Because most of the ethanol in this country is produced from corn. So you pay the corn growers to produce corn at below market price, and they sell it to the ethanol producers. They produce ethanol, and they force us to put 10% of it in our gas tanks. It's not good for your engines, but the manufacturers of internal combustion engines have been working to make them more tolerant to ethanol. Okay, methanol is another possibility, right? But you have the same situation as ethanol. Seed oil is another possibility. The diesel engine, right? Everybody know how a diesel engine works, right? Internal combustion engines, the gasoline engine has to spark. So we compress it about 6 or 7 to 1 compression ratio. And then you hit it with a spark, it blows, pushes the piston down. In diesel engines, they're compression ignition. We've learned from our gas laws that if you compress a gas, it gets hotter. So you compress it instead of 6 or 7 to 1, you compress it 15 to 20 to 1. And that compression makes it so hot, then you inject the fuel into that compressed air and it immediately ignites. And the original diesel engine created in Germany by none other than Diesel himself was designed to run on vegetable oil. We only started using petroleum products because we didn't know what to do with that fraction. So we said, oh, let's try it in a diesel engine. Yeah, it works. But I saw a program one time where this crew wanted to travel across the country in a school bus that had a diesel engine in it. They didn't want to spend any money on diesel fuel. So they'd stop periodically in towns and go to fast food restaurants or sit-down restaurants and ask them if they can have their waste oil. Right? So they didn't have to pay to have it shipped off and recycled. So they got this waste oil of vegetable oil for free, and they put it in a tank in the back of their bus, and they ran their diesel engine on it. The only thing you have to do is preheat it. If you don't preheat it, then it'll turn into gel in your lines, and then you're stranded. Okay, here's the problem with photovoltaics and with wind, right? Besides the fact that they are only available intermittently, you've got other problems. We don't have storage capacity for the energy they produce, right? And the economics are not competitive. This is another case where government subsidies make these photovoltaics and wind energy projects viable, right? What do they say? If you want more of it, subsidize it. If you want less of it, tax it. That's the way the government controls our economy. So it has uncompetitive economics. It would not survive on its own. And besides that, most of our photovoltaics and wind turbines come from China. And that's a strategic problem too. That's because, at least for the near future, they have a controlling interest in rare earth metals, which are essential for making those magnets and for making the photovoltaics. Environmental hazards. Okay. When you produce a photovoltaic cell or a wind turbine motor, you produce waste, right? And I'm not talking about just like extra carbon dioxide. I'm talking about toxic stuff, because you have to take a ton of rock and crush it and extract these rare earth minerals that may be only 0.01%. So you got all that waste you got to throw away. Then at the end of life, because these things only last a certain while, like any technology, they wear out. What do you do with them? If you're not efficiently recycling them, then they fill our dumps. And there's another environmental hazard. Nuclear solves all these problems for the foreseeable future. Nuclear is the answer. And there are companies that are feverishly working on ways to develop fusion power. Okay, and they're having some success. There are a couple of instances where they've actually exceeded the amount of energy produced from the reaction. It exceeds the amount of energy it took to initiate the reaction. Right, that's the breaking point. Now they need to be able to scale it up. Okay, we're done. So that means on Thursday, we'll start the review, and we don't have to finish on Thursday. We can go to the next Tuesday. And that would be Thursday's the 26th, Tuesday's the 3rd of March. And on that day, we can finish our review and then go in the lab to do waters of constitution and hydration.